we are moving into the session of efficient and effective data analytics, starting with Antoine Basset from CNES in France.
Great. Good morning. Today I'm going to talk about something which was already touched on by many speakers yesterday and not necessarily named explicitly, which is efficiency of the processing. Technically speaking, this is part of performance assessment, but this is a very specific subset of it. We've heard a lot how processing demand is exploding. This will continue. But I believe that there is a huge gap between demand and the actual need. The answer to that, obviously, is optimization, and efficiency targeted optimization is probably one of the best ways to reduce this gap. In the meantime, resources are limited. Infrastructures are growing, but slower than the demand. In this context, performance, parallelization, technology are not enough. What we need is efficiency, or in other words, it's roughly equivalent to greener IT. This is the key, and this is the key everywhere in the processing stack. It's the case, obviously, on the infrastructure side, but up to the mission level and the processing strategies in the projects. So today, I will not have time to discuss all of this. I will illustrate efficiency issues or opportunities at some levels of this stack. But first, I would like to define those terms, performance and efficiency. Performance is something quite intuitive. All of us use this word for various measurements, assessments, like we want our pipelines to be fast and lightweight somehow, to be robust, and so on. All of this is necessary, obviously, it's fine, but it's not sufficient. And what we need is complementary measurements to reach efficiency. Those measurements are things you may be familiar with, like scalability and adaptivity, for example. And they have in common that they all relate somehow to a ratio between actually used resources and available resources. So this is my definition of efficiency. If you do not waste the resources, you are efficient. As you see, they come with drawbacks, which means that you should not focus on efficiency everywhere. Instead, you have to tackle that where it matters, where it has an impact. And for that, you have to identify the bottlenecks, the contentions, and to benchmark. So that's already a tricky part, how to detect where you have efficiency issues. It's quite complex. Let's move on to some examples I've seen from my previous projects, from low level to high level. So first one will be quite technical. Feel free to fall asleep now and wake up later if you're not familiar with development. So big data processing, in particular, is built on ND arrays and dimensional arrays. They are everywhere, and they are stored linearly in memory. Okay, memory is something very linear. How do you do that? Let's take an example of an image, a matrix. The most common way to store it in memory is to unroll it row by row and store those rows contiguously in memory. And now what we are going to do with this image is transpose it, okay? We flip the axes. There are two natural ways of doing so. Either you move the pixel values in memory, or you change the indexing scheme. Instead of unrolling row by row, you unroll column by column, okay? Let's do this. I have 3 variables, and I will make 2 very complex operations. A plus 80 call and A plus 80 row. Okay, exactly the same complexity, exactly the same amount of additions, and here is the result. So in the first case, it's 10 times slower than in the second case. Why? The only difference is memory management, okay? In the first case, you have two matrices which do not line up well in memory. Therefore, when you loop over them, you have to jump back and forth in memory to reach the pixels. And that is extremely inefficient because memory is slow. And this is much worse for GPUs, for example. Second illustration, parallelization is something which is known to be an extremely good tool for performance. If you want to go faster, you parallelize, okay? But this is something very inefficient in the sense that you waste resources. Why so? Let's take a classical example of a pipeline made of jobs, themselves made of processes, and themselves made of threads. At each parallelization level, you introduce overheads. Those overheads are wasted resources. Sometimes it's bad, sometimes it's not. You have to assess that. In any case, the more branches, the more parallelization branches, the shorter the wall time, but the more wasted resources, right? In addition to that, in general, inside the pipeline, the number of parallel branches must vary. You need 60 cores at the beginning, then 6, then 1, and so on. Therefore, you should adapt your booking to your needs, and you should also adapt inside your jobs the resources you are going to consume with respect to what your system gave you. And this adaptivity is absolutely key. Here is a real case example of a pipeline with dynamic booking. So you see the booking in orange and the actual usage in blue. And this is a good example, okay? Here we have already 25% resources lost. Those are resources which are not available for other users of the computing center. That's not a problem when you're alone, but when resources are limited, when the center is busy, then this is simply lost. Thing is, if you do not run in parallel, you waste nothing. It is more efficient. Then there is a balance, obviously, to be found. Sometimes it's not true, because you have to find other balances between resources to avoid contentions, for example, but that's another topic. It's just an illustration. Final illustration on the mission level. So we all have processing strategies in our projects. A typical one is a dual strategy where you have, on one hand, on-the-fly processing. You get data from the satellite or from another pipeline, you process it. This helps improving the algorithms, getting output, showing output, analyzing that. And when you want to output the data release, then you need to reprocess in batch mode. And in general, you do it several times to get a very mature and glorious data release. All of this is fine in theory, but in practice, how many times do you reprocess a data, and how many times do you process a data and do not use the output? That's the vast majority of the cases. Here's an example for 2 missions. It's out of reach to any human analysis. So you process everything that comes in, get results, process with the next pipeline, and so on, and at the end, it goes direct to trash. Why? Just because you had this strategy. You could define other strategies, like pick only a subset of the inputs by default and process on that. And before clicking on the button, just think twice, do you really need to process this? Oops. Sorry. Yet again. So, good morning. Okay, last slide. Efficiency is not only necessary when you have large processing, it's necessary when your demand is higher than what you have at hand. That's the case, obviously, for big data and greedy algorithms, but that's also the case when the resources are very limited. I mention here video games because that's a very leading field for efficiency-targeted design, and there is something called data-oriented design, which is at the heart of optimization targeting efficiency. It's something fascinating. It's also the case, obviously, for onboard processing. We are talking about putting AI on board. How do you do that? By making codes efficient. Then you have to take efficiency in the process. How do you apply that? It's throughout the life of the project, including design and operations. So you have to think globally and keep resources and efficiency concerns in mind at every step. As I said, you have to benchmark a lot. That's key. And finally, to learn. Once you have benchmarked and you know where the problem is, how to solve it, then that's another topic, and I have no time to discuss it today. Before I thank you, I would like to recommend 2 books to the programmers here. First one, most of you know it, I guess. If you do not want to buy it, at least read the table of contents. It's free. And if you read the titles of the sections, you understand 99% of it. Second one is about data-oriented design, and it's completely free in PDF format. It's very fun, so read it as a novel. Thank you.
Thank you, Antoine. I think that we have time for questions, so I don't know if there is any in the audience. Okay, not that I have one question. Yeah. And in your paper and in your presentation, you talk about optimizing the software development to the architecture, the physical architecture at all levels of the, let's say, the software stack. And sometimes in science, with scientific data from space and Earth observation and so on, many developers are only focused on the development of pipelines and so on. So do you think that it will be possible to define some metrics, high level, that could be easily understood by developers so they take into account that? Yeah,
there are such metrics, they exist. It's generally not easy to assess the value. But they exist, and then each case is different. That's what's difficult with efficiency. It's very specific to your use case. So that's why it's better to have it in mind while designing, while developing, than later, because it's difficult to go back, benchmark, find the issues, and correct.
Okay. Yeah. Thank you. So if there is no other questions, I think that we can go to the next speaker. So the next speaker is Stefan Kimmler from DLR in Germany, and he's going to present the paper analyzing big data workloads using discrete simulation. So please go ahead.
Yes, thank you very much. So it's a big title, so I repeat it: Analyzing Big Data Workloads Using Discrete Simulation, a work that has been done at DLR, German Aerospace Center. So we hear all along of this conference that many Earth observation applications work on really huge amounts of data, actually. And for that purpose, these workloads produce, or they need also a lot of resources in the IT infrastructure. So compute resources, network requirements, network links, very high bandwidth network links, and also storage, online storage resources and compute power. We hear also a lot about cloud infrastructures and high-performance computing services that actually provide these requirements, or provide help to leverage all that. And this is actually great, because in that way, our application, we can just scale up. So in order to work with even higher workloads or higher volumes of data, or also in order to achieve our application targets in time. However, that has also a drawback, because we may end up with suddenly very surprisingly high costs on that. And did we talk about energy efficiency somehow, and what about our carbon footprint? So the idea here behind this talk and my contribution to this conference here is to go one step back, to look at the system that is supposed to run a big data workload, and to use model-based simulation in order to find out, well, could we somehow optimize the system maybe, in order to optimize the resource consumption or also to predict the service performance of our application and maybe also the total runtime. So model-based simulation is mainly composed of 2 steps. So in the first step, we're going to develop a model of the system that is supposed to run the big data workload. And for this, we use usually a tool, a simulation tool. And in this tool, we are able to build up a model of our system that is composed of different elements. So there are static elements like components of our system like storage, hardware, compute nodes, maybe also memory we may model, but also our application software. So for example, a processing algorithm that has a certain behavior or complexity. And there are also dynamic elements like a data set, a data unit, a data entity that is flowing through our system, and also a workflow that is composed of steps that handles these data elements. And then in the second step, we'll use this model actually by configuring it. And it's a key issue. And based on this initial configuration of the model, we will run simulations. And we do this in an iterative approach. So again and again, and this is also called what-if experiments. So we change the initial settings of the model, we run the simulation again, look at the results, and even during a simulation run, we are able to look into the details of all the model elements to see where can we do some optimizations. So to look a bit more detail into the first step, you see here a typical static and dynamic model elements. For example, a network link that has a throughput, a latency, or also a processing algorithm, as I said, is handling a certain data volume. And there are two very important things that you need to consider when building such a system model. The first thing is you have to model also uncertainty. Because as in the real IT world, I would say, a load is never constant. A network bandwidth is never constant. There's always a probabilistic distribution of whether it's faster or not. And so this is very important to take into account. And the other point is the so-called gray boxing approach. So you will never be able to model your system to every bit and pieces. That's not possible, it's too complex. So you need to take your experience you have some background experience where you know, okay, that part of the system has really impact on performance. So then you can detail the system model there where you know that there is impact on performance. On the other hand, you can course your model where you know there's less experience, or you have less impact on performance issues. So that is also a very important aspect when modeling. Now this is very theoretical. Let's look at an example. And the tool that I have used for this to prepare this work here is a simulation tool called JamSim. It's an open source tool that was built initially for factory simulation and simulating physical flows of physical items in factories, for example. But it turned out to be very suitable also to simulate IT systems and digital systems and data flows. And the example here is taken from an atmospheric mission where we have a lot of Earth observation data from an atmospheric sensor. We have to reprocess that data, so it's that reprocessing scenario. Many years of data to be reprocessed, and the part of the model that you see here is just the downloading of input data into this reprocessing infrastructure, which is a cloud-based infrastructure. So downloading it from a remote long-term archive using an ingestion system. So what we do here in the model, for defining that model, we define the relevant components. These are interlinked, so we have, for example, a wide array network. We have an ingestion system, we have online storage, and we have also main entities that are used to run in this simulation. So for example, we have a product entity, has a certain size, and we have requests. Then we detail the system model where we expect to have impact on performance. In this case here, it was the request workflow running in this ingestion system and also the data handling part where the ingestion does some metadata extraction, maybe reformatting, work on the data, things like that. And then, as I said, it's important to include also uncertainties. So in this example here, we took some wide area network breakdown probability. Also the length of a breakdown of that network is modeled. So that brings us these uncertainties. And once now this model is designed, we go to the second step, and this is the exciting part of the work, is to run these experiments. So we start with a certain start configuration. We parameterize our model. We launch the simulation. We run it using the tool. We can also stop the simulation, or we can accelerate the simulation, which is very important because such a reprocessing campaign take days, weeks, even months, maybe, or a year, up to a year, maybe. So you need to speed up to be able to look at the results in due time. And then, of course, we can see where are bottlenecks. And in the best case, we go even back to step one to refine our model of the system if we saw that there is some bottleneck somewhere, or even there's a component that is somehow underload. Again, in the example, so the simulation looks like that. Here we start now with a certain set of input parameters, and in this exercise here, we tried to look especially to the ingestion cache size, which is here one part here within the ingestion system. So we start the simulation with an initial size of 100 gigabyte, and we wanted to see how is the impact of this cache size to the overall ingestion performance. And we launched the simulation in this tool. This is the screenshot of this tool here, where we can also accelerate the simulation. And in this tool, you are able to select each of the components in the tool and to look in real time how the component behaves. So how is the load, how is the length of a queue, how many products are already on the online storage, and so on. And the tool also allows to have a graphical view on the change of that of these values. So we are able to plot here, for example, the ingestion rate of products ingested per minute. And when starting with 100 gigabyte cache size, we see the ingestion rate, okay, goes up to 10 products per minute after 20 minutes of simulation, so in real time. Now in a second experiment, what if experiment, we change that size to 10 gigabytes, so already drastically down, and we see that the ingestion rate behaves quite similar. So there's not a lot of impact. We just see, if we look close, that this time that reaches to go up to this 10 products per minute just takes 5 minutes longer. Now we can even go again down to 3 gigabyte ingestion cache size. Still the curve looks acceptable. However, if now we run the simulation for a longer period of time, we will see there will be a wide area network breakdown, for example. And in this case, the processing will somehow stop because there is no input data available anymore. So we should not go too low with that, and run also the simulation multiple times with different parameters. So that was just a very simple example to illustrate that. And in order to conclude, these are my takeaway messages for you. Using big data workload simulations in order to prepare real system configurations can significantly save resources. So if you have a big workload to prepare a big data workload, it's worthwhile to think about that. However, there's an issue with the models, because it's very hard work to develop good system models, valuable system models. It requires really a priori experience that you need to have. And of course, you need to include uncertainties, a very important topic. And if you have exaggerated the system model, it looks like in this figure, so don't exaggerate it. And finally, running iterative simulation experiments is really fun and exciting once you have the model. And it can also reveal unexpected potential for system optimization. That's actually my personal experience with that. Yeah, I'm happy to have also an online demo here right after this session. If you want to have a look, and can demonstrate some other aspects of this simulation tool. Thank you for the attention.
Thank you. Are there questions from the audience? Yes, there's one.
Hi, thanks for the great talk. I have a question. Is there any plans that you, in the future, once the system that has been modeled is put into place, and you to ingest again some profiling logs or some profiling data into the model from before to kind of reduce the uncertainties or improve the parameterization?
That's a very good point. So actually, the exercise that we made, it was also a posteriori. So we had the big data workload already, and we had all the logs and information in order to feed the model and to configure how, the model. So yes, that's I think a good exercise to do that actually. So on the tool, you have to look what are the capabilities of the tool. For example, the tool has an API, so this Java Sims tool that I mentioned has an API. So there are ways to interact with the tool, yes. But of course, it's quite some work also to feed back your results into the tool again. But it's a very good idea, definitely, yes.
Thank you.
So thank you, Stefan.
Yeah.
For more questions, I heard you're available in the demo area
Exactly.
at 10:30.
Thanks.
So with this, welcome to our next speaker, Anne Fouliou from the Simula Research Observatory in Norway, talking more about Pangeo at EOSC.
Yes, thank you, and hello everyone. So I'm not the most important person on this slide. You have many other names, Tina, Alejandro, Sebastian, Lorenzo, and Guillaume, and this is a community activity. So I will first repeat again maybe what is Pangeo, and you may not know what is the European Open Science Cloud, so I will also give you some hints on this, and I will explain why. Why do we want to have Pangeo at EOS, so the why and the how, and how we can use it, and why we think this is important to have infrastructure as a service, as explained by Ryan. And then why we also thought it was very necessary to have community of practice to regulate or to discuss on how we can best use this infrastructure. So what is Pangeo? And I think here this is a summary of what is Pangeo. This is a worldwide collaboration. This is all about people. And I think this is the best summary we can give about Pangeo. There are many logos here. I'm missing many of them. It's very hard to have everyone on one slide because it's community-driven. And as Ryan said, it's a bottom-up approach. And this is why it's working very well, because it's driven by the needs of the user, and we can get feedback directly from what we need, what they need, from developers, from the scientists, and from the software engineer and the infrastructure. So what do we do together? Pangeo is all about integration. There is no one Pangeo software, as we already mentioned. It's a modular, open, and scalable platform. It can be deployed everywhere, on the laptop, on the cloud, and on the HPC. And depending on where you deploy it, you will have different components. But we always have a data model. It's based on XArray. Many of you are using XArray. You have a user interface, and we like to have interactivity with Jupyter and BiDS'. And then you will have a storage system, which may depend, can be like a Lustre on an HPC or Amazon S3 compatible object storage if you are on the cloud. So it can be different. You can cherry pick, and you can scale. If you need scalable compute, maybe you have Dask or Beam. Maybe you don't need on the laptop. And then if you have scalable compute, you need to have resource management, such as Slurm, maybe on a HPC or Kubernetes. So this is very flexible, and this is why you can prototype on your laptop, you can move maybe on the cloud, and you can scale on the HPC if you need to. So we know what is Pangeo. But so what is the European Open Science Cloud? And here I have to read it, because here this is not a bottom-up approach, it's a top-down. It's coming from the European Commission. So the ambition of the European Open Science Cloud is to develop a web of fair data and services for science in Europe with federated and open multidisciplinary environment where researchers can publish, fund, and reuse data, tools, and services for research, innovation, and educational purposes. And here, FAIR stands for findable, accessible, interoperable, and reusable. Whew. That's a long sentence. Yes, and I can highlight the word ambition. Yes, ambitions fuel the journey, but action lights the way. You need action. So you need top-down and bottom-up, and you need to merge and to meet somewhere. And this is a why. This is why we have Pangeo at EOSC, because we need to have action. We need to realize this European Open Science Cloud. So Pangeo is an infrastructure agnostic. It makes it a great use case for EOSC and other federated clouds. When you use XRA, Dask, or Jupyter notebooks, you are essentially part of the Pangeo community already. So Pangeo serves as a glue, as a facilitator for deployment on various infrastructure. It is open source, it eliminates vendor lock-in risks, and at times, this is why we want to have it on the European Open Science Cloud, we need to be on European infrastructure. So when we have research grants, we can only ask and request services on European infrastructure. This is a must from the founders. And this is a federation of infrastructure. If we want to have a federation, we cannot have only one centralized infrastructure. If you want to be interoperable, you need to have several infrastructure, and you need to understand what are the problems when you have more than one. So now we know the why. What is the how? How do we do it? Well, we don't reinvent the wheel. We just reuse what is available. And there are already a lot of things, because the Pangeo community is maintaining a lot of things already. So we reuse what is existing, what has been done, for instance, by 2I2C for the Pangeo deployment configuration. We use the same, and what you have in the middle, I don't know if I can, yeah, here, is what is maintained by the Pangeo community. So you can have this Jupyter Hub, your Binder Hub, with a bunch of packages, or Pangeo notebook, machine learning, with TensorFlow or PyTorch. It is cloud agnostic. You want to be able to spawn it, to deploy it on any infrastructure. So we can do it on CryoDios, on Chestnut, we can use on OpenStack, on Amazon. It doesn't really matter. You can move where you need to, where you have resources at a given time, and maybe you want to do some part of your computation on one cloud and do another part on another cloud. It should be transparent for the end user. What is very important for EOSC is what is at the bottom here. We need to have authentication, something easy for user, not to have 10 different ways to authenticate to a service. So we are using the EGI check-in, which is a way to, it's like a proxy for several authentication providers, including, for instance, LinkedIn or GitHub. And this, as a service, is no more than what you could have without EOSC, but you can choose on EOSC who is accessing your service. So it can be also not necessarily free, it can be paid service, but it is under this umbrella of EOSC, which means researchers can access this infrastructure and they can have it in their research grant. So how do we use it? So we realize if you have a Pangeo infrastructure as a service, this is great, but people need to learn how to use it. So one of the most popular services is this Pangeo training infrastructure as a service, where you can deploy on demand a Pangeo infrastructure with different configuration depending on the number of participants, and they can learn how to use this infrastructure. So we have, for instance, made the training on FOSS4G. It's very short, and they are only learning the basics. And what is very important is we also try to streamline how you develop or how you collaboratively develop and deliver training, having best practices on defining good learning objectives, trying to meet these learning objectives in the training material so we can help to raise the level and people are optimizing the way they are using the resources. We can also do similar courses, but for students at university, it's very similar. But here, for instance, they will work in groups and they will work on mini projects, so they will go a bit further on how you can use this infrastructure and how you can exploit Earth observation data or climate data, depending on what they do. And if you have researchers, usually they need to scale. So if you need to scale, you need, for instance, to use DASC. But they need to learn how to use DASC, because if they don't use it efficiently, they are wasting resources, and there is no point to have this fantastic infrastructure. So this is what we are trying to do, and all the training material is always CC by 4. It can be reused by anyone. And if you have been here on Monday, we had a joint collaboration with OpenEO, and we deliver together a training material on scaling big data analysis with Pangeo and OpenEO. Because again, it's about collaboration. And if you want to request Pangeo training infrastructure as a service, we have a small Google form. And if you want to deliver yourself, you can use and we can spawn this kind of infrastructure. So we have the infrastructure. We can teach how to use it. But in fact, outside the training, you want to work on your own work, your own research, for instance. And for this, we realize there is a need coming from the community to have a community of practice. You need to have best practices. You can write fantastic Jupyter notebook, but if they are not reusable and not shareable, you can reproduce science just on clicking and rerunning all the cells, but you cannot reuse it to build upon them. So we are, again, not reinventing the wheel. We team up with another initiative. We team up with the Environmental Data Science Book, which is an initiative led by Leandro Coca-Castro. And here, the goal is really to provide best practices on how to write notebooks and how to review and collaboratively review notebooks. So we are trying to give some guidance on how they can best modularize their Jupyter notebooks so they are reusable for others. And then we have like a gallery of Jupyter notebooks where you can browse and you can reuse because they are fully reproducible. We use this approach in the Climate Informatics Reproducibility Challenge, where again, we provided the Pangeo training infrastructure as a service. We also tried to reproduce scientific paper from the Environmental Data Science Journal from the Cambridge University Press. And all the Jupyter notebooks created by these teams, they didn't know each other. We formed teams on the fly. They were peer-reviewed, and they were published in the Environmental Data Science book. And as you can see, there are many, many collaborators, because collaboration is key. So I will conclude here. Being on EOSC, on the European Open Science Cloud, is not an option. It's a must. You can say, I don't care. But researchers will have to go there to get the resources. They will not be able to pay for private cloud if you are not on EOSC. But you can be on EOSC if you are a private company. It doesn't have to be free. We can put it on the research grant. There is very little overhead to add Pangeo on EOSC. It's mostly adding AGI check-in. And of course, when we talk about European, we need to go far beyond boundaries. It's not only for European researchers, it's for on European premises, on European infrastructure. We really want to get your input for the next step to develop a roadmap. I see many of you are using some of the components of the Pangeo ecosystem, because we really want to better serve the communities and increase the number of diverse users and developers. So diversity is also very important. And finally, my last word is I really want to promote EOSC, and I really want to convince other Earth observation data and services provider that you have to go to EOSC and put your services so researchers will be able to use them. And that's it.
Well, thank you, Anne. I think we have some minutes for questions. I don't know if anyone in the audience wants to ask something. Okay, I have one. It's an easy one, because I was like stuck in your third slide, or fourth, I don't know, where you say that you are like sometimes limited to European resources, to use European resources.
Yes.
And do you have like any kind of roadmap or ideas to improve this dependency, or to, let's say, to make it so the resources are the same level as the one that you have in other regions? Or, because if I understood well, when you are to process, no, in your slide you said that sometimes you are limited to European assets. So I don't understand what is the.
So what I mean here is when you write a research grant, if, for instance, in your National Research Council and you're asking for funding, one of the requirements is to either use university infrastructure, national infrastructure, or EOSC infrastructure. We cannot choose other infrastructure. It's a must. So if you are not on EOSC, it means we can only use what is available to us, and we are missing a lot of great stuff.
Okay.
So this is why we would like you to come.
Okay, understood. Thank you. There is one question there, yeah.
Thanks, Anne. Also great talk. If I put that together with what Ryan said and think about what federation means and hearing your last words about EOSC, I would say my conclusion is, how can we get away from branding individual clouds to branding the cloud, the federated cloud? Like we talk about the internet, we don't talk about the offer of this and that. And I think we need to find a different branding for these cloud services, maybe more specific than just internet. But in a way, I think one of the problems really is that we keep advertising specific clouds. You talk about the EOSC, we just launched the CDSE, there is Destination Earth, there's all these things that kind of do all the same on the different branding, and in the end, they all talk about federation, but they have not yet found that bracket that keeps them together. So how do we get there, and how could we call that?
So first of all, I think if you take the analogy of internet, internet is for everyone, but we all have different providers. And it is okay. This is what we want here for the cloud. It is okay to have different cloud providers. It is okay to have EOSC or whatever they want to call it. But at the end, it should be available maybe at different cost with a different business model to everyone. So there is still, and this is what also Ryan mentioned, if you want to have this layer where we can interoperate, we should first to admit that we need to have a federation and we need to interoperate. And to interoperate, it means you need to go to the other one and check what they do. This is why we are inviting you to come to EOSC, because you have no clue, I'm sure, after my talk about EOSC. I'm sure you don't know what it is. If you come, then you will understand. And if I come to you, I will understand what you do. And this is the only way to have interoperability. Interoperability is what you don't know. It's the ignorance or your blind spot, and you can only know if you reach someone else that doesn't do exactly the same thing. I'm sure I haven't replied to your questions. What? Well, we started. As Pangeo community, we went to EOSC. And we are happy to start with you. Please talk to us. We will go and reach you. We can start, because as I said, Pangeo is really grassroots, and we take action. You are not convinced.
Well, I think that we can continue this discussion in the coffee break afterwards. So thank you very much, Anne. I think it was very interesting. And we go to the last presenter of the session today, who is Tina Odaka from the Laboratory for Ocean Physics and Satellite Remote Sensing in France. So please, Tina.
Thank you very much. And thank you for having me today. So I'm Tina. So as she just introduced, I'm from Laboratory for Ocean Physics and Satellite Remote Sensing in an institute called IFRAMER. So IFRAMER is an oceanography institute. And with the colleague from this lab, and also from the colleague from different department, which is a biologist, Matthew Warris from the DECOD lab, Ecosystem Dynamics and Sustainability lab, we made this study on Pangeo for studying fish movement using biologging and earth science data. I think this is a big data from space conference, so I think biology is a bit far. So I try to be more I try to explain more about why biologging is connected with this conference, Big Science, Big Data from Space. So first of all, why studying the fish movement? Our motivation is for the food security and sustainable exploitation of natural resource. So we need to study how fish movement and migration shape the internal dynamics of populations. And this knowledge is, as you can obviously see, is crucial for improving the fishery management and then to define the conservation areas. There is the International Council for Exploitation of the Sea, called ICES. They state the lack of information regarding the fish spatial structure and essential fish habitats. So to study this fish movement, we use biologging. So what is biologging? Biologging is attaching small devices to animals. And then we track their behavior and then try to gather the environmental data. But as I just said, we are studying fish. How can we track these devices underwater? Unfortunately, we cannot put the GPS. We cannot send the data after the data, like what maybe you've seen this argo with sea lions in the head or something like that. Fish is too small, it's really underwater. We cannot do that. So our solution is that we use two kinds of tag, data storage tag and acoustic tag. And the data storage tag, it stores the time series of observed temperature and depth in the tag. Acoustic tag, it emits a signal, and then we detect the fish using acoustic telemetry network. So what we do is we combine both tags together with earth science data to infer the fish trajectory from individual environment data and the history using like geolocation models. So this, to a bit change the, from satellite to the little animals, this is how we tag the fish. So we collaborate with the fishermen. They know where the fish. And then they will catch the fish, and they basically make them sleep. And then we put this acoustic tag and data storage tag. We let them a bit rest, and then we release them. So then how do we collect the data? The collection of data for the data storage tag is done with the incentive program. So we mobilize the citizens in the recovery of the fish tag. So as you can see this poster there, this is something that where we are in France, we see in the port where there is a professional fisherman or like recreative fishermen there. So we tell them, check when you fish the fish, check if there is these 3 blue tattoos on your sea bass or pollack, and then if you find this tag fish, first note the date. and the location, latitude and longitude, super important for us. And the weight and the length of the fish, and then contact to our institute. So if they come with full fish, they get 100 euro. And if they eat them, and if they come just with the tags in the body, they get just 50 euro. Or like next time you come to the holiday in Britain or in the English coast, or sometimes we even found the tag even in the Spanish coast. So check it well. If you see this red data storage tag, call us, you will get 50 euro also. So even though you don't do fishing, you have a chance to get, and you have a chance to participate in this study. Yeah. It's kind of amazing because we had, so in InfraMed, we have these two projects since 10 years. So for this BiDS' project and Fish Intel project, we tagged more than 1,200 fish. We got more than 500 tags coming back. So it's quite nice, huh? So in this 500 tag, we have the temperature and depth time series. I think I should go fast, right? We have only 3 minutes. Oh my God. So in this time series, we have the time series in situ observation, like everybody knows, right? So what we do with acoustic tag is like acoustic tag emits the unique identifier. So if they swim next to this black dot, it's the detector, we know where the fish passed. So using this biologging, the time series data, we combine them with our science data, and we study the likelihood. And then as we know the constraint, where we release them, where we detected in between, where we captured, or also the fish cannot go more than the bathymetry, so we calculate that to using a hidden Markov model, and we make the simulations. So this is software for tracking reconstruction. The quality of this track that we can calculate, it depends on the resolution and the quality of our science data. So it is crucial for this model to have high resolution and high quality earth science data. And the original, so this model being made like by biologists like 2008, but this original software which was deployed on our HPC center in 2016 was not at all scalable to really deal with the high resolution earth science data. And if we look at how they work, basically what they do is accessing in situ observation environment data, accessing big earth science data. We make calculation on Python, and we make something with a visualization. That's really familiar for us. So that's where we end up with teaming up with the Pangeo community. So we try to, the importance is like we don't want to reinvent all the software from the scratch to make it scalable, but we just want to reuse the Pangeo software stack to make this tracking program work. So in this Pangeo fish software, there are several important aspects that we used on the Pangeo. I think some of you already saw what is a care chunk and intake and some poster presentation. So it's a possibility, as is ZA, it's a cloud, you can access to this, the cloud, access these data through cloud. What we made it possible is using this Audatis infrastructure, which is stayed in InfraMed. We made our all the reference data, which is Copernicus, and some internal InfraMed product, which is available of every hour for many years. We basically made it possible to access it, although the data is on the HPC, from HTTP, from internet, or even from the inside, the same data without copying it to, for example, S3. We made it possible to access it using Intel and care chunk. And we save our intermediate file in ZAR format, and then we optimize this HMM model using task and number to make it scalable. And we can run this model on a local PC or HPC or on the cloud. Other work we did was Pangeo fish, because the model is based on convolution. And when we make a convolution, we need to overcome the challenge related with a unique cell surface area. To do so, we introduce hill peaks using hill peaks, which is a part of the grid system called the GGS. If you're interested, please listen to the lightning talk this afternoon. I will put the link afterwards. And for the visualization, for the biologists to interactively really click and zoom and see the data, we use HBplot or XMovie to make some movies. And this the graph is one of the examples that we gave for the biologists to study the track that we computed. So this is our perspective. So we made this development. We want more biologists to use it even outside InfraMed. So we submitted the project to Destination Earth Service Platform as a use case. And thanks to that, we accepted as a use case called Global Fish Tracking System in collaboration with Similar Research Institute and Development Seed. And then this studying about how to select data, this also led us to make another project which would be profitable for Pangeo community in collaboration with CNES. And also this HillPix implementation that's led us to the sprint in the BiDS'23 this time. And then there will be so we made a collaboration with our Pangeo community, for example, Ryan or Alex over there, and also Peter. And then the draft implementation will be presented this afternoon at 4:40. So to conclude, we developed a general tool applicable to other fish biologging data. So we could show some synergy between the biology and earth science data community by using the common open source tool without reinventing everything from the scratch. And what is important that as a takeaway message is because we're doing it in open source, the development that we made on our side will be back on this geoscience community also. So it's really the synergy that we can make it, doing it in this way. So that is that is all from me. And I just want to thank to this TAOS project, which funded internally and InfraMed to make it possible to work two departments, which is normally not working together, really to collaborate and make this happen. Thank you.